Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, it's my pleasure to introduce Bob Briscoe. He's from BTE, he's chief researcher. He has done a bunch of work on congestion control, and he's going to talk about some of that today. Okay, so you're starting.
All right. Okay, good afternoon. I was just saying I'm a bit zonked from being at the ITF last week, and it's just suddenly hitting me. Anyway, let's get going. Well, firstly, thanks to Murari for inviting me, and I think he's going to turn up fairly soon. He said he'd be a bit late. So, firstly, I need to know, if I say things like ECN, will everyone in the room know what it is, or do I have to sort of, I don't know how much I have to.
There are other people listening.
Yeah.
So you should probably explain your terms.
Yeah, there is potentially a number of people listening who are very
Okay, so I mean, I've tried to keep it fairly, not baby, but sort of.
But they can't make faces at you, so.
Try to explain my context, but I'll do it briefly for some basic stuff. So, this talk is about sharing the capacity of the internet, and this is a summary of the full talk, where we sort of thought that TCP's job was to share out capacity as well as doing congestion control. Because it had this emergent property where it made what was called fairness, where window fairness, where the amount that each TCP took from a bottleneck was approximately equal relative to its round trip time. And so overall that was considered a good way of sharing the internet, where good was defined by some sort of engineering approximation. And actually, it turns out, if you look at what a good way to share out capacity would be from an economic point of view, that would be very wrong, the way TCP shares it out. And that's saying nothing about the dynamic response, that's fine. But what's actually happened is, because that's such a bad way of sharing out the internet from an economic point of view, that means from a competitive point of view, from one ISP to another, they've been trying to change the way capacity is shared out, forcing their own view of things on the world, silently overriding what TCP is trying to do, using some variants of deep packet inspection or volume capping or all the rest of it. And so what we're ending up with is an internet infested with blocks and throttles, and that means that anything new we try and do won't get through, anything big may not get through either, and it's all getting a bit of a mess. So the goal of my research over the past few years has been to try and work out what would be a common agreeable goal for both networks and hosts, or we should really talk in terms of the stakeholders, networks and the customers of those networks. That started by trying to explain why TCP friendly wasn't a useful concept. TCP friendly being this, each flow getting approximately equal rate if it's got equal round trip time. I think we've got a fair way in turning people round now, reversing that consensus, certainly in the transport area at the IETF anyway. And a guy called Matt Mathis, who's just about to join Google, he's been at Pittsburgh Supercomputer Center for many years, 30 in fact, and I are leading an attempt to rewrite the capacity sharing architecture at the IETF, at least in the IRTF, and then eventually we'll bring it to the IAB, and you may want to have some say in it. You may want to have some say now. Right. And the main point is that capacity sharing can't really be dealt with at design time. You can't just design a protocol and then expect it to be used and somehow the capacity magically gets shared, because it all depends how much data people put through that protocol and how many of those protocols they run. And so you can't just say a priori that this is going to be fair from the design of a protocol. So it's a runtime point. So the approach we've been taking in our research is, yes, still get the host to do the high-speed detection of congestion and variation of their rates, but give them tip them in the right direction with incentives, so that they weight those congestion controls. That's weight, W-E-I-G-H-T, not slowing them down. And then you've got similar dynamics but different shares, and you give them the incentive to set those weights to be in everyone else's interests, and you back those incentives by enforcement if they don't keep to them. But you try and keep the end systems working cleanly, and you only introduce the enforcement if you need to, but you make sure if it does kick in that it doesn't screw things up as well. So that's the overall flavour of the whole thing. So it's quite important. It's really something that was never got right from the start, I'm claiming, and it's a plugging a hole that's been in the internet for so many years now that we've lost the ambition to try and fix it. And once you do fix it, you find a lot of other things get sorted out, is my contention. So where have we got to? The next couple of slides just give you a bit of the status of this before we go into what it is. As I said, since 2006, the support for the way TCP shares capacity in the transport area has collapsed. We had a straw poll in the transport area about a year ago now, and to the question, is TCP friendliness the way forward? 0. Not necessarily consensus on what is the way forward, but certainly TCP isn't. And I think we've got one of the few directions for a way forward, but I wouldn't claim that we're universally supported and everyone's behind us. But there isn't really another major tradition. Just last week, we had a second attempt to get a working group going on the approach that I'm going to describe in this talk, called congestion exposure, to get a working group going called CONEX. It requires additions to IP v4 and v6, so it's pretty contentious. And the argument was that there's enough people wanting to do this that it's worth picking up the last bit in the IPv4 header for this. And we got a sort of no, not yet. So what we're going to do is work on v6. We've got a hacky way to do it in v4, so we can do some trials and things. And then if we get enough pressure behind it, we could come back and go for rechartering to get changes in v4. But we may find actually that the hacky way is actually clean enough that it will just survive and we won't need to do what we were originally intending. So there's a number of individuals who've offered help on this. That list of companies, by the way, isn't formal support from those companies, individuals in those companies, and like Mirari's been helping out, which is why Microsoft's on the list. And you can see there, there's about, of the people who've said they want to help, there's maybe 60% from industry, 40% from academia. So it's getting some traction. The other thing that's going on, more at the top-down level, we got approached by, in fact, the vice chair of this organisation called the Global Information Infrastructure Commission, GIIC, happened to be the CTO of BT. He's now the global CTO of Huawei, and he's still vice chair of this organisation. It's a sort of smoking, can't say smoking men's, smoking people's club of CXOs, CEOs, CTOs of the major corporations, ICT corporations, and they get together to look at proposals coming from various parts of the world to try and make the world better, in some sense, and they try and put their weight behind it. So we were asked to put forward a proposal as a way of making the internet better, particularly for developing world, for capacity investment, etc., as well as solving some of the problems with net neutrality in this country that we're standing in now, or at least some of us. I don't know whether anyone else is remote. And they said, okay, this sounds cool, let's do a proper review of this. They got in people from various stakeholders like BitTorrent, AT&T, they got Dave Clarke in, to assess this. People, public policy point of view, from the academic world, commercial point of view, technical point of view, and the report on that was published in January. There wasn't really anything negative at all in it. It was quite a favourable report. So they were giving strong support, and they're now in the process of writing a manifesto. So this is gaining traction from them as well. And then there's been a load of media coverage as well. So I'm just saying this is building up. One of the neat things about the media coverage, if you go and look at any of these articles in some of these papers that have picked it up, if you were to have an article in one of these things about broadband speed, quality, pricing and net neutrality, you would expect the blog and all the postings to be completely flaming and all the rest of it, but they're actually really reasonable. Somehow this proposal seems to turn on people's reasonable switch, because I guess because it sees things from both sides. So anyway, what are we talking about? Yep.
Can you talk about why MIT's communication futures, what they're interested in?
Okay, yeah. In fact, they helped a fair bit with the people that were called in to review this. So David Clarke wanted to help when he found out about this proposal because he saw it as a good way to tidy up the internet a fair bit. And so we have there's a group called the Communications Futures Program based in MIT, which aims to remove blockages from the industry that are examples are privacy, security, identity, things like that is one working group. Interconnection between networks is another. And this one was picked up as a subject for the interconnection working group, which I now co-chair through the fact I'm pushing this. And we're writing a white paper on this together on a roadmap for deploying it. And David wanted to put some resources into this to try and make it happen. Okay. So going back, why is TCP friendliness not the answer first? This is how some people think the internet sharing works. If you're a networking person, you probably think it's all done with fair queuing and things like that. And if you're a transport or application layer person, you probably think it's all done with TCP. So just imagine there are two flows going through this bottleneck. For now, two could be N, a green and an orange one from these two machines. And what they do, TCP ramps up, halves, ramps up, halves. Whenever it experiences a loss, which are those little stars, it's meant to halve. And that loss may be due to it hitting the edges of its own pipe or hitting another flow. so once the orange flow starts, they fairly quickly converge on about half the pipe each. Now, of course, it relies on voluntary effort, so if something comes in that doesn't respond to the others, it can just sit there and push through. Also, if the green guy opens 4 flows, he can be 4 times as aggressive as the orange one. He'll get 4/5 of that capacity. But much more subtly, people always focus on this sort of number of flows thing, but just the amount of data you send clearly has an effect. You know, if you're going on for longer and someone else comes in and a number of you are going on for a long time and a few flows aren't going on for a long time, they've just got a tiny bit of data to send, they won't get any credit for having not been there, right? When in fact they could quite easily be given more capacity while they are there without affecting the other guys, right? And you know, the numbers are quite large. Peer-to-peer, 5 times more flows maybe than other systems. I mean, web's now getting up to 6. You know, maybe some are pushing the bounds of that. And we ran up BitTorrent on 8 bonded DSLs, and it opened up 100 flows from various sites when they were all when the seeders were all free to do that. So and then if you're talking about maybe 200 times more data, you're talking about in the thousands or even 20,000 times higher traffic intensity just by gaming the system, if you like. And so I would claim that this is broken. You know, we haven't really got a fairness system that's making the internet work well. And there are a number of approaches other than TCP that are actually going on underneath, and quite often they're fighting. So these diagrams, you'll see the sort of, that's a summary of the previous diagram where all those saw teeth there I've just smoothed out into rectangles just to make it easier. And so fair queuing will, if this one's per user fair queuing, whenever there's more than one flow, it will just give them half each. Well, 1/nth each. Volume cap I've tried to draw. It's a bit difficult to draw that one. Essentially, it's counting you out in over time, integrating the bit rate over time to get the volume. And once that's run out, then other people get more capacity. And so that's what's showing there with the orange guy suddenly getting a lot more capacity. And then various other more sophisticated, in quotes, approaches. Deep packet inspection, it's nearly universally used in the cellular industry. It's nearly universal in the UK. I don't think it's that common in the US. Maybe 1 or 2 companies do it, other than the cellular area. And largely what it's doing is picking on particular applications, usually at peak time, throttling them down, possibly even putting them into a different diff-serve class internally in the box. And it doesn't necessarily use up all the capacity, because it's having to effectively create a false bottleneck on its own box that's trying to mirror all the other bottlenecks in the network. So it's trying to manage capacity without actually knowing what's going on in the real queues all over the rest of the network by making itself the bottleneck. And the point I made on the previous slide is what we really want, which is where there's no reason why flows that are lighter can't go faster, and then the green guy won't finish that much later than it would have done before, modulo some dynamics, having to accelerate more and decelerate more. And the orange guys will get very much faster completion times in the process.
But it's not just waiting for a queue, high rate, something else.
That note there says that isn't necessarily done in the network. This is I haven't said how this is done yet. This is what we'd like to see, and what I'm going to talk about is whether the end systems can do that, given the right incentives, rather than having to do that in the network. And one of the reasons for that is that each router, each switch, doesn't necessarily have a full view of what a particular user is doing. And so I'm trying to move towards an edge solution.
On the volume cap,
Yep.
Is that just a desperate attempt to fix the congestion problem even though it actually doesn't fix congestion, or?
Yeah, that's a good summary. It helps a little, but it constrains you too much when you don't need to be constrained, and not enough when you do, really, because it's not really solving the problem at peak times. And also in a network, peak time isn't just like the 5 hours in the evening. It's measured in milliseconds, then it goes away for a bit, and then another millisecond. So ideally you want something a bit more sophisticated. You really want these solutions to be working like fair queuing on the queuing timescale, because that's the timescale that all the systems are using the network, and you need to be thinking about incentives for the systems rather than just the humans. Yep. Right, so starting now to build up towards what the solution is. And firstly, I just want to sort of say congestion is not evil. It's and particularly signals of congestion are not evil at all. They're potentially healthy signals of approaching congestion. Firstly, the reason congestion isn't evil is that it shows the system's being used to its maximum extent. And you can't tell that that's happening until you've just got a little bit of congestion. So a little bit of congestion is good for you. Right? Take it 5 times a day. And the neat trick, as I hope everyone knows, explicit congestion notification, which was an update to IP back in 2001, at least the proposed standard at that point, where as the queue builds, you mark more packets, you end up getting a tiny queuing delay and a tiny loss for all traffic, a really tiny loss, sometimes 0 loss. On systems where we've been running ECN for a long time, we seriously haven't seen any losses. And effectively what you're doing is you're seeing congestion signals, but you're preventing any impairment. You're not getting any delay, or not appreciable delay, and you're not getting any loss. So congestion really then does become something that you can't say is evil. It's just incipient congestion. However, the gains from ECN seem to have been too small to overcome a number of deployment barriers, some of which actually you guys have presented at the IETF. Yeah. And I guess most people here know about them. Yeah. Yeah. And they weren't the first barriers. I mean, there was firewalls before that and all the rest of it. These things take a long time. So having...
Well, do all the links in the chain have to be congestion aware and provide sync?
ECN aware, you mean? Not at all. No, ECN is designed so that the packet says I'm ECN capable, which means that any link that is ECN aware can mark it, but any link that isn't ECN aware will just drop packets when it's congested. So
It has to not crash.
they have to not crash when they see that marking. Yeah.
If only both ends are ECN aware, that's just not good enough. That's not different than...
Well, it's a start. I mean, at least then the network operator can't say, oh, I'm not going to bother doing that because the end systems aren't doing it. It means that the first one to deploy in the network will actually have some effect. And we're currently in the position where I think all from Vista, all servers had ECN by default, but the clients off by default. From Vista, the clients were off by default, servers on by default. Yeah, Is that?
If you negotiate, you get it, but otherwise we don't negotiate. So.
Yeah. 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 If a server's on both ends have to support it for it to get turned on in the data packets. And similarly in Linux now, since May last year, servers are on by default, clients off. But that's not quite enough. So another theme of this, a background theme to this talk is that I'm going to use ECM for something else than what it was originally intended. And it may have a lot stronger incentive for the network operators to want to do it and for everyone to want to do it because it's to do with fixing this capacity sharing problem. And it all comes from the recognition that the way to determine how much those orange flows should push into the green ones comes from an understanding of how much congestion they're causing or contributing to. So I'm going to argue for this metric called congestion volume as a metric that we ought to be using to share out capacity. Now, all congestion volume is, the simplest way to think about it is to just understand how you'd measure it. And if you had ECN turned on, it would be the volume of bytes marked by the ECN algorithm. So it's like ignoring all the bytes that weren't involved in congestion. It's just measuring the ones that were. Yeah. So it's a strong signal of which bytes were coming through the system when it was congested. So, for instance, in this case here, where you've got, let's imagine you've got the system varying between 0.01% congestion in the lean times and 1% congestion in the congested times. Just imagine it's a square wave for the sake of argument. So when the orange guy is going through, he's only sending 300 megabyte in those periods, but the other guy's sending even less just in those short periods when there's 1% marking, if you added it all up over a long period. So 1% times 300 is 3 meg, 1% times 100 meg is 1 meg. So the orange guy is causing 3 megabytes of congestion volume, the green 1 megabyte. But in the other periods, the congestion's much less, but there's a lot more data sent in those periods, so 0.01% times 10 gigabytes is 1 megabyte. So overall, the green guy is contributing 2 megabytes of congestion volume, and the orange guy, 3 megabytes. So actually, the green guy is causing less cost to the system, if you like, than the orange guy.
When you say user at the top, do you mean flow or machine or user or what?
Right. The idea of this that it's meant to be a contractual entity, and that may be, the family in the home. It may be a corporate network, maybe another ISP. Yeah.
This is an aggregate number of flows coming from the same
Yeah.
organization for some definition.
Like volume can be measured from anything that's a entity. It's a similar type of measure. It's something you measure crossing a boundary rather than a rate or whatever of a flow. Because you would measure it by just counting the marks crossing that boundary, or counting the marked bytes and ignoring all the other ones. So it's like doing a net stat, but ignoring the...
You don't care about distinguishing flow A from flow B?
No, yeah.
Okay.
Right.
Keep this at every point in the network.
Well, the idea is you only need to measure it at the trust boundary between, where one network is connected to another, or when your home is connected to a network. It's just like if you had a volume cap, if an ISP was setting volume caps for their customers, you only need to measure it where the traffic crosses. Right.
Are we thinking about these congestion volumes in megabytes per second?
No, it's actually,
time?
it is congestion hyphen volume. It is a volume of bytes. You can think of it, you can sort of then average it and say, well, that congestion volume over a month, you could divide it by a month and get it into congestion per second, if you like, and that would be in bits per second, but it's probably easier to think of it just as a volume. Yeah.
So in your little picture in the top right, does that mean that it's cumulative? So the congestion volume for orange would be 3 times one thing by the time you got to the right?
Yeah. And that was the idea of these diagrams. The 300 megabytes was the total of everything that was sent during the 1% times. Yeah.
During the set of 1% time,
Yeah.
not during
Yeah.
each one.
Yes.
Yeah.
Yeah. During. But you know, you don't have to do all this if you just have a marking algorithm and you count those marked bytes. That's what happens. I'm just trying to break it down to explain what's going on. All right. And so that gives a feel for, if, say, for instance, the orange guy had a 4 megabyte allowance and the green guy had a 4 megabyte allowance, then they would have over some time, they would have some incentive to start behaving a bit like that. Yeah? Where and what we're trying to do is incentivize the sort of things like leadbat, which would do that sort of thing, where when it senses congestion, if it's got a lot to send, it will back away because it knows that if it keeps on being aggressive all the time, it will sort of kill its own allowance.
This means you could be an unresponsive flow as long as you haven't used any bandwidth this month, right?
Yeah, exactly. Yeah.
Sorry, so you're changing the marking probability as a function of the number of flows, or?
No, the marking probability, I'm not changing the marking probability from what it happens to be anyway, but if you put 4 TCP flows through a queue, the marking probability will be, well, you can calculate it from the TCP formula because you know the capacity divided by 4 is the TCP flow, so you can work out. In fact, with TCP, because it's 1 over root P, where P is the marking probability, and if you've got ECN turned on, if you put 4 flows through there and then you put 8 flows through there, you'll get not 2 times the amount of congestion, you'll get 4 times the amount of congestion, you'll get the square of the congestion. So if you put 10 times more flows through a bottleneck, you'll get 100 times more congestion, assuming you don't go into a regime of TCP that becomes where the formula blows, which you probably will by the time you... yeah. So yeah, the reason the congestion goes up is because there's more aggression going on. Effectively, those orange ones are behaving like many TCPs. Yeah. And the green ones, they're 4 separate flows, so they're behaving like 4 TCPs. Yeah. And as a little aside, one of the goals of this as well is to avoid marking rate inflation, where everyone tries to push in front of everyone else, whereas it actually becomes beneficial for the green guy to be less than 1 TCP, if you like. And so you don't always end up leapfrogging each other. So hopefully I've explained that. Congestion volume also has a really interesting economic property. It's also related to, and in a perfect market it's equal to, the cost of the capacity that would have been necessary to avoid having had the congestion. Right? So, sort of, I've shown this. If I had to upgrade that silver pipe to the blue one to avoid that congestion, just conceptually, that would have been the same. So the cost of that congestion volume can be related to the capacity you'd have had to put in to get rid of it. And so that shows another reason why ISPs may want to do this, because the only thing that costs them is congestion. If there's no congestion and the network's half full, making it 60% full doesn't cost anyone anything. It's all been invested in. It's sitting there. It's not harming anyone else. If there's 10% more utilization, although that does mean there'll be a little bit more congestion, but that's a detail. So it's got a sort of dual nature where it's both the amount of congestion that customers contribute when they're sending too much traffic, and it's the amount of congestion that the ISP causes by not putting in enough capacity. It's sort of dual blame, and you can't say which one is to blame. Right? Now I wanted to we haven't done enough runs of this to say this is accurate, but I wanted to try and explain that congestion volume and volume aren't good proxies of each other. So if you know that you've got a high volume user, it doesn't necessarily mean they're causing a lot of problems. So this was taking traffic exiting Naples University, doing looking at the TCPs only, because they were the ones that were easy to analyse, and measuring how much loss there was. So this is the amount of volume each user sent. Each dot is a user.
Is user here a machine or really a user?
This was machines, because it was a university. We sort of...
So user is an IP address?
Yeah. So IP address. Sorry, those dots are IP addresses. And the vertical axis is the amount of bytes that IP address lost. This was over 3 hours. So that was the amount of data that was lost from that flow through somewhere on the end-to-end path. Not necessarily just in the university, but somewhere in the path. And as you can see, the volume ranges over 5 decades, and the loss does as well as the amount of bytes lost. And if you pick one of these high volume users, they may well not be a high congestion volume user. So if you were to say, right, we're going to hit those guys hard because they're sending a lot of volume, you're actually getting most of them, you're getting the wrong people. You should be getting those guys, right? They're the ones that are costing because they're sending their volume at the same time as other people are. And that's what goes on if you look at queuing timescales. So interesting data, but I just want to emphasise it's not totally sound. Yeah. Right. Now coming on to something that's going to be happening over the next few years. You've done compound TCP as a future congestion control. Other people have done other attempts, cubic, etc. And really what we're trying to solve as we go into the future is a scaling problem with TCP, where this is TCP and this is what a more scalable TCP should do. And that's what we got today. So I've got to work through this, and then I'll explain the bullets. There's quite a lot to this slide. So at the moment, this is a flow in congestion avoidance shown in the bottom of these diagrams. And at the top, what I'm trying to show is that on top of that, you get other flows arriving. And when flows are in congestion avoidance, if they're all competing with each other, they're all hitting each other, and every time there's a bit of a loss, one of the sawteeth goes down, and then another one gets a loss and the sawtooth goes down. But you also get those losses from the arrivals of new flows hitting the end of slow start, right? And so the way TCP scales requires the loss recovery time to get longer. The sawteeth get bigger, basically. And that's what it would like to do to get up to a higher window here. It takes a long time to get there, and then it falls a long way, and then it takes a long time to get there, and it falls a long way. And everyone knows that's wrong, but it's not often really appreciated what is wrong about that. And the problem is you've got other things happening, like new flows arriving, and as we scale to bigger networks, we're not going to get less flows arriving. We're going to get more, if anything, or at least the same. So as they keep hitting, they keep beating it down, and it never actually achieves its potential. And that's because it's become too sensitive to any single loss. Whereas if you can keep it so it's got the same loss recovery time as it had before, but a faster window, then you can scale. And that's what, there is one called scalable TCP that ensures that the loss recovery time stays constant no matter how fast you go. So what I'm trying to argue in the rest of this slide is that as we move into the future, we've got this arbitration to do between flows going on over a long time and flows trying to get started fast. And they have to accelerate into an empty network. They have got no information until they hit the top. And then if they've been accelerating up with some sort of exponential ramp up, they're going to hugely overshoot. If they're in a big aggregate, they're going to cause losses all over the place and knock everyone down continually. And so we need some way to arbitrate between just those two phases, not only that, but also between elastic flows and VoIP and all the other things. But we need some way to understand how the effects of one transport affect another. And I'm claiming that congestion volume is that, based on the original work of Frank Kelly, who did an economic optimization of a network based on congestion volume and showed that if you allowed all the flows to have different responsiveness, then you could get an optimum social welfare out of the whole system. Right. So that, taking account of the congestion you cause each other, the new overshoots, and what I said at the start, just how many bytes you're transferring and how many flows you're doing it in and all the rest of it. Just something that will take that all into account, but as a bulk for each economic entity using the system. I think I'll skip over this in the interest of time because we've got one or two more to go. So ideally what we want is to be able to measure this thing called congestion volume as traffic enters the network. That's where we currently measure volume. So I'm proposing as a thought experiment, if we could mark our packets before they entered the network, if the sender could mark them, these little black ones, to match how much congestion they're going to experience, then what you could do is have some sort of contract like this where you have an allowance of how much congestion you can cause in the rest of the whole internet that feeds this bucket. Every time you put black bytes into the network, you remove the equivalent amount of tokens from that bucket. And only if you empty that bucket does it start limiting how much you put into the internet. And so if you're going on this one, which has no congestion on it, you can just carry on even if you've got an empty bucket. But if you're in a high congestion path, well, that's the highest one on the diagram, you'll have to limit yourself. Your software will be incentivized to limit itself. And similarly, at a human level, you will discover that if you always do everything at peak time with really crap software, that you won't get as good an experience as if you are a bit more sociable.
When you say limit somebody, are you limiting all of their connections, or are you talking source address pairs, source destination pairs?
How that policer is implemented is not so important because, I mean, well, it depends how the ISP wants to do it. I mean, if I were designing that, I would just limit them all because you wouldn't normally expect them to hit the limit. So it's the equivalent to asking, well, should we put a mint on the pillow in the guy's prison cell? You know, it's sort of once they've broken the rules, do you really care to treat them well? You know, it's.
Is it only the destination that knows about the congestion?
Right. So I'm saying this is a thought experiment, and then I'm going to tell you how we do it.
Okay.
Right? That's what ideally we'd like to do, is to be able to limit things before they enter the network. Because if we had that policer at the receiving end about how much congestion I was causing by what I received, then it would be an obvious denial of service target. You know, I could just throw congestion at you and run down your policer. Right. You know, the control is at the network layer is with the source, so we need to limit that initially, or at least we need to be able to. And as it says at the bottom, yes, this would be nice, but the internet wasn't designed this way. the network can't actually see this congestion, and particularly if there's drop and you're using IPsec, you can't see the gaps in the sequence numbers if you just look at packets going past. If you're on a router that's dropping packets, you know you're dropping them, but you don't necessarily know, across your whole network, you haven't got an easy way to manage that. And you certainly don't know what's going on in other networks. So the solution to this problem in high-level view is a three-step process. Step number one, ECN on the routers, and also potentially on the switches in the lower layers, or you just design things so that most of your congestion is at the IP nodes. So I'm showing that as putting these little -1 flags on, because I'm calling ECN debit marks. Then receiver feeds back to sender whenever it sees one of those red marks. And that's, so far, everything I've said is all what's in the ECN standard, the proposed standard, RFC 3168. The novel bit is the black bit. So when the sender, every time the sender gets some feedback, it reinserts a mark on another color into the data flow. So it tells the network what congestion it's seeing from the feedback it's getting, which I'm calling re-feedback. And this protocol is called, consequently, re-ECN, so reinserted ECN. And one of the neat features of it is that if you look anywhere in the network, over time there should be no more red marks than black marks. So if he isn't playing the game and he's understating how much congestion he's seeing, you will see an excess of red marks and you'll be able to punish him in some way. Right?
Is this only for TCP, or is there
No, it can be
path, right?
Yeah, anything with a feedback path. And in fact, even if you haven't got a feedback path, as long as you're conservative about it, for instance, something like a broadcast, a multicast streaming digital fountain or something like that that doesn't have any feedback at all, as long as you put enough black marks in for normal congestion, you'll cover yourself. Or if you get the occasional bit of feedback that just gives you a little bit of information, then it's better than nothing. You've just got to make sure there's more black than red. Yeah. Does that answer your question?
I don't follow yet, but maybe as you go through it, maybe I'll follow.
Right. It's, obviously, it wouldn't be. What essentially it does, it makes it in your interest to have enough feedback to know what the congestion is. And if you don't know, you have to be conservative, because the network deal is that if you don't put as much black in as red, at least, then you're liable to have your traffic dropped because you're lying.
But what you showed on the previous slide is where the ingress router has no idea how much red is later in the path.
Doesn't matter, because the only rule is that the black has got to be greater than the red, which it is there. It's only when you get to the end that it gets more serious, because you've got all the red has happened, and then you've got to make sure if the black has to be greater than the red, it has to be sufficient to cover all the red that happened. But it doesn't mean to say that the black is still greater than the red there as well.
The idea would be distributed enforcing, right? So at ingress, there's something that checks to make sure that I'm not putting more black marks on than I should. If it does, then ingress.
It doesn't matter if you put more black marks in than you should. Less is the problem.
I guess what I'm saying is that there's my carrier, my first hop ISP is going to make sure that I'm just not putting black marks on every packet, right? It's going to hold me to sort of whatever.
You're saying black marks slow you down.
Yeah.
So by putting in black marks, you're being nice to others.
Yeah.
You're saying you want to make sure they don't put in less black marks than the red marks, which are the drops they get.
Yeah.
Now, if you don't have your own feedback path, then it gets really hard to put any marks.
Well, he's saying you just put in some amount of marks and hope for the best.
Yeah.
Yeah.
But that's.
But you because of that previous, if you've got that policer there, the more black marks you put in, the more you're going to risk being policed. And so you want to minimise the amount of black marks to the actual black marks if you can. And if you go any lower, you risk some detector at the egress to the network picking you up for cheating. Yeah, is that? It's sort of a you're between a rock and a hard place, if you like.
How does the egress point know how many how does it know how many red marks happened prior to it?
Well, they're in the traffic. It has to. It would have to store a balance of red and black.
Is the red is markings, not drops, right?
Yes. Yep.
So these are on the headers themselves?
Yes.
So
And that's
what prevents someone from changing to whatever they like?
who's someone.
A router, or I don't know, some man in the middle. I mean, if I were to be punished by the number of red or black headers that I have, and these are in the header, unencrypted, I'd assume.
Yep.
What would keep them authentic?
Right. So say a network wanted to cheat. I mean, my whole thesis was about all the different possible ways people can cheat, and I did a PhD on this, so, and part time, and why everything is everyone has an incentive to be honest to everyone else. But just briefly, just take one example: a network. If it wants to deny that congestion is happening, then if it doesn't mark packets, the sources will still send fast at it, and it will basically collapse. It will not give a good service to everyone because it's not telling them that they've got to slow down, right? And you'll end up getting drop instead of marking, and then you can't really hide a drop because you have to do something. If you've got to drop something, you've got to drop something. If it's wanting to increase the amount of marking, it can do that, but then it just slows everyone down. And so it really only wants to put in congestion when there is actually congestion. Now, there are other cases where, say, this network was congested and then it comes past here. Can that one remove the congestion, remove the marks? And that incentive is sorted out by settlement between these two based on the amount of congestion between them. But I'm going, that goes on quite a bit further than I was planning to do in this talk, but just sort of, you'll have to go and review my thesis.
So you don't have any case where there's both a black and a red mark on the same packet. I'm assuming
You can do.
The black packet is you remove the black mark and leave it unmarked.
No, actually, the markings are orthogonal, so that you can have both.
Is there a reason for them to be orthogonal as opposed to just...
Yeah, the original encoding had them non-orthogonal, and it introduced an attack that the network could do it because it could essentially bias its marking to always mark packets that were already black to game the system. It could knock out a plus that the user had put in and gain rather than...
What's an intermediate router?
Pardon?
An intermediate router could? Or?
Yeah.
So I don't understand the distinction between... it can always overwrite the black mark anyway, so I don't understand the difference at the end of the day.
No, the black mark is in a field that doesn't change all the way. It's immutable across the system, and so the transport can actually tell if it's been changed.
The transport can tell if it's changed?
Yeah. So the sender, if it chooses, the sender and the receiver can ensure that they can check if the sender has set it black, that it appears black at the other end.
Okay, sorry, we're playing about a game now, but what if I preferentially drop the packets that have the black marks in them, and then some other network downstream gets to be the bad guy and actually do the enforcement, but I gain the benefit.
Right, so let's, I think I thought of this one. Yeah, I did. I was just trying to think what the argument is against it. So, this guy drops the black ones out.
Yeah.
And this one then says, you are obviously cheating, and starts dropping packets.
Suppresses that flow.
Right.
Why would you drop packets? You might not reach the congestion threshold. guess it depends on how many packets you drop.
What is your
Because
goal
those
in
packets
dropping the
are-
packets?
Yeah, that's what I'm wondering, because you don't really gain anything because you're killing one of your own customers.
You gotta drop something.
No, but it's your own service, it's your own customers that
Yeah,
you're dropping
yeah.
packets to. I mean,
Well, no, the idea is I'm a transit network now, right? And so
so you're,
if there's
Yeah,
some
but
class of
only-
traffic-
the way this
some
works
class of
is-
traffic that I want to prefer over some other
Sure.
class without actually
Yeah.
somehow, I still want to be more conserving, right? I want to keep all my links busy.
And I would prefer my customer's traffic over
To
somebody else's
else's,
customer's
yeah.
traffic that's coming through me.
Right.
Okay.
Right.
So if you
Yeah.
drop packets, you might not even cause congestion at the next hop, in the next ISP. Because you drop packets. There are fewer packets entering there.
That's true.
Yeah. So then what's the problem?
So which,
If the guy down the line is getting congestion because you're just one of many different contributors to it,
Yeah.
then that flow gets blamed. Right?
I've lost the scenario here because what?
imagine,
All right, well, let's talk about that.
We'll
Sorry,
we'll talk about it at the end, why don't you go through?
Shall I carry on? Yeah.
Yeah.
Okay. Right. Right. So all I want to do with this slide is show that there's one other feature you can get with this. So this goes into a bit more detail by saying, well, let's imagine that same scenario. This was the picture we had before with the little red and black flags, with the packet stream going between these networks. And now let's imagine that some of these little flags are being introduced a little bit by one router and then most of it by this one here. I've drawn them negative for a reason because they're debit and the other ones are credit, but obviously that's just a question of definition. Now, the idea is then that feedback goes back, as I said, both those were standard steps already, and then the new bit is this one marks 3% of the packets black. Yep. And then if you take black minus red as you go across the path, you'll get that blue line. Now the neat thing is here, the small amount of congestion that was visible in red packets passing that border, when you subtract that from the larger black, you get 2.6, which is the amount of congestion that's going to be caused. It's essentially saying that's the black is the whole path congestion, subtract what's already happened and you get what's going to happen. So you can then use that for settlements between networks. And so if I understood the case right, this network, if it were to have a relationship with this network, that then becomes its customer. So, you know, it's always bilateral relations with the customer next to you, and you know how much of the congestion is one side or the other of that boundary by looking at the traffic. Yeah,
How would you
is that?
expect to work it for settlement if there's more congestion downstream? You send me packets, most of the congestion's downstream, so therefore you're going to pay me less per package you give me because I'm giving you a bad path? Or you're going to pay me more because, oh, I've got all this congestion?
Yeah, this is, so in economics, congestion is like the price. It's saying the supply is low and so the price has gone up. And so the competitive economics would say that this guy pays that guy for the congestion in that network, or in that network and beyond. Yeah. And so this is the difference from a volume metric in that the metric actually changes as it goes through the network. And as you guys seem to be slightly interested, I've got a spare slide that shows if you just count all the black minus all the red across a border, it's effectively the same as counting the cross-sectional area of each of those steps. And these steps are those blue steps I showed in the previous diagram. And the depth into the diagram is the bit rate of each of the flows. So it gives you a measure of all the congestion being caused by all the sources behind that boundary with just measuring in bulk. Right? But you know, I'm not saying how anyone should use this metric. I'm just saying it's useful to have the metric, you know, and because it's a measure of the economic cost of traffic. And so competition should drive the providers to use it. There's a little sketch of how the dropper would work that I mentioned at the end that was at the egress that is looking at whether the amount of black and red match. And the correct way to do that is to take the proportion of the two, so in this case 2/3, and remove that amount of traffic so that you make the amount of red equal to the amount of black again. But you remove the amount of other traffic as well, and that creates the correct incentives for them to have put the right amount in the first place. Right, this is actually a neat bit that I don't often talk about, and I know I haven't got much time. In fact, I've got negative time, I think, now. Do you guys want me to carry on? Or so, yeah? Yep, okay. There's an aspect of the system where everything's always slightly late. The feedback always comes one round trip late. So the rule I worked out that would make the system prevent abuse is that the source always has to take the risk on itself of what it might cause. And so it has to, and I invented another colour for this, I'll call it green. So it's the new black, right? So it's a credit, but it's a pre-credit that you put in on your SIN and on your first data packet, and actually we worked out the first and the third data packet will cover the risk of the slow start and the markings at the end of the slow start if you're using TCP. And then you always have to be just ahead. Or the rule the network makes is that I don't then have to give you any leeway as the network. I don't have to allow one round trip's leeway. It's you that has to put credit in advance, and so I can always be absolutely precise that if you ever go negative, I will start punishing you, because I've got a stateless network and I can't hold state on this. And it also has got some quite neat properties. It becomes a way of doing flow state management on servers and middle boxes, and it also is the key to mitigating DDoS, because DDoS causes congestion, and you can actually prevent it from causing congestion, or at least mitigate the congestion back in the polices at the beginning of the network. But I'm not going to cover that whole area now, because DDoS is a complete slide set. So this is a more arm-wavy slide that just ends it all up by saying that just with this one change, you create a whole cascade of effects throughout the stack. That's an hourglass if you hadn't noticed. And just by changing the internetwork layer, by revealing usage costs, the ISPs don't any longer have to do all this deep packet inspection and stuff to try and infer what costs different applications are causing. The transports, although they could see the costs, the significance of those costs are made clear to them, and then they can change their behaviour to take account of how much they're harming other people. Also, even in the MAC layer, down in layer 2, that's effectively about sharing capacity. And what this signal now gives you at layer 3 is a way to see what this capacity is causing in the whole internet network, not just the local link. And you don't need to do sharing separately in just one link, because you can manage that as part of the congestion of the whole system. And so effectively this visibility of congestion in the whole system allows you to, say, manage a cable network or a PON and drive the input queues into that. And there's, I mentioned DOS. What else can you have? I suppose one that's worth mentioning is QoS, quality of service. You just sort of get automatically by, if you want to go faster, you just go faster. That's QoS, right? All the queues are short because ECN's made them short. And if you want more bit rate, you just go faster, and you can. QoS done, you know. And if you go too fast and cause too much congestion, you'll get stopped. But you don't have to worry too much. You don't have to sort of mark packets and have contracts and all the rest of it. You know, it's just all part of best effort, but it's a very good best effort. I call it best without effort. So this is my final slide. Just
before you get there,
yep.
back to the question about is this per source or per source destination?
Right.
This would be a fundamental question, right?
Right. Yeah.
If I'm going over some high-priced link, congested link, at the end of the earth, BT or AT&T doesn't want to penalize that customer, explain to that customer why they're now used up all their tokens.
Right.
So you wouldn't want to lump. It seems like you wouldn't want to. You're not correcting the right behavior. If you want to steer people away from the expensive link, if you steer them away from everything with just source-based control.
Right. Source-based control is the default here. What I wanted to do was get the source to be in primary control, but that doesn't. The benefit of how fast it goes accrues to both itself and the receiver. You know, and if the receiver is sitting behind an expensive link, I think is what's behind your question.
Yeah, and so let's say every now and then I go to Human Black Bread's website, Hong Kong. It's a really congested link. I use up all my tokens there, even though basically it doesn't hurt anybody. It just hurt the others going to that one website. It didn't hurt.
But that has that shows there's demand for that's greater than the link capacity.
Right.
And so effectively what will happen is, which goes back to that spare slide I had with the routing money, the allowance that you've paid your provider, some of that will work its way through the system to that site in Hong Kong, which will have the money to upgrade its link. It's effectively like putting a millicent on every, where it routes the money to where the demand is higher than the capacity. And that's what the system is trying to do. It's trying to say there's demand here and there's unmet supply. That's what congestion is. Yeah. So it's actually intended to do what you're not wanting it to do. Yeah. Yeah.
So there's still one more. I've finally been able to, I think, explain one of the things that's confusing me. I asked a question earlier on about, what's a user? Is a user is it a machine or a flow? You said, well, it's an organization. It's the thing that the enforcing entity has a peering relationship with. Yeah. So what I'm concerned or confused about, or perhaps somewhere in between, is where you have somebody that's cheating, and so the sender has the equivalent of 100 red marks and 0 black marks.
Right.
And the traffic manages to get a couple hops through the network over towards the receiver side one. The guy in the receiver is looking at it, and by that point has lost all distinction about this particular flow or sender as opposed to 100 other ones. So from the receiver's perspective, he says, I have 10,000 black marks and 10,100 red marks. Mm-hmm. Okay? So I end up penalizing everybody 1% rather than the bad guy a lot.
Right.
Do you follow that?
Yeah, I do. No,
am I confused or?
No, you're exactly correct. And so the idea is that where there is a discrepancy, if it's in a large aggregate, if you are looking in the middle of the network, you probably do that on some randomized basis, it tells you to go and look closer. You don't necessarily drop everything immediately. It says, there's something suspicious here. I want to delve in and find out exactly which one of these flows.
You may know which peer it is, and it tells you which transit provider it came through on the receiving side. It says, well, it came through, AT&T's network.
Yes, but what I mean is if you then say, right, I've got a problem in this aggregate, if I now pick out some flows from that aggregate, I will find the one that's wrong. And if it is all of them just a little bit, then you can, because the packets, if you compare the packets in any flow.
So then you are having to put it back into deep packet inspection stuff.
No, it's not deep packet inspection. It is per flow inspection at that point, yes, if you wanted to do it there. But the you don't have to do the dropping. I'll get with you in a minute. You don't have to do this anti-cheating mechanism everywhere in the network. It's sufficient to just do it right at the end.
Actually, I would think that this cheating checks need to be done every time I enter and exit any provider.
But that assumes that there's not incrementally deployable. Here you want there to be some incentive, even if you only deploy it in one spot in the network. And so in the example I gave, the only spot that it is deployed is, the first guy that does it is the guy that's close to receiver. And at that point he has an aggregate, he's got stuff from 10,000 flows coming in, and one of them is cheating, and he ends up penalizing all of them 1%.
Yeah.
But I'm proposing that close to the receiver, that he would eventually do per flow.
Hopefully,
right.
Hopefully you're saying that hopefully that happens on a small subset of flows, that he has some way of figuring out. That's going to be hard though, in the example that he gave.
Yeah. You're saying if you start looking at an aggregate,
having to constantiate per flow state is expensive.
Oh, I know. I mean, okay, so yeah, maybe I didn't say that. This needs per flow state, but it doesn't suffer from the fate sharing problem of flow state. So there are two problems with flow state. One is the cost of it, and the other is the fact that it causes a fixed point in the network that requires that state. And this one suffers from the cost problem, but not the fate sharing, breaking fate sharing, because if you reroute, the state just recreates itself on another box, because every time there's a black mark, it's just like soft state, but it's automatic. So yes, there is a cost of flow state in this system in order to police it, and I can't get around that. Hands up, right? But it's not deep packet inspection. It's in the IP header.
But you're hoping that flow state is happening at the absolute edge.
Yeah.
So the number of people that's getting out at that point is hopefully smaller.
I'm hoping it's manageable. I mean, the absolute edges are still quite large, but it's
sure.
Yeah. In terms of cost, we use. I don't think I'm allowed to say how many deep packet inspection boxes cover our customer base. I'm going to have to. We use 32 deep packet inspection boxes for the whole country.
When I say deep packet inspection versus header stuff.
Yeah.
Right?
That's what I'm getting to.
A flow is everything coming out of a single ISP. Then you're right. Only the IP header is sufficient.
Well, no. I mean, for all this, only the IP header is sufficient. The only reason I mentioned deep packet inspection is because they do flow state as well.
Right. So I was assuming that you would do deep packet inspection so that you could distinguish between, say, all of China Mobile. It's actually customer number 1 versus customer number 2. Because if you assume that all of that is behind a single mat, then just the IP header, the IP source address isn't sufficient to distinguish anything larger than the very large ISP.
Well,
So that's what I meant by deep packet inspection. I was guessing you'd actually want the 5 tuple.
No, the way I've tried to design this is so that if my customer is China Mobile, I don't have to look anything further into it than China Mobile. They look at their customers, where their customers.
The example I gave is where you're the receiver, and you got lots of sources scattered across a huge ISP, Comcast, China Mobile, BT, whatever. But that organization hasn't yet become re-ECN aware.
Right.
And so that out of that entire organization, the receiving end says, well, I got 10,000 black marks and 10,100 red marks, and so I penalize the whole ISP 1%. And there's actually not an incentive for the bad guy to be doing the right thing, because 1%, hey, I can pay 1% as long as I can go through.
It's the combination of the 5 tuple. It's not just the source.
Right. But you can't get the 5 tuple without deep packet inspection for some definition of deep.
That's true. Yes.
Okay.
That is true. And if it's IPsec, it would be the SPI or whatever.
Right.
Yeah.
What does the network do differently with something with a packet with a black mark on it versus one that doesn't?
It just counts it. That's all at the policer. And That very
Your charging mechanism took into account black marks.
Will it preferentially drop it, or will it?
no.
It'll get counted against your congestion volume.
Yeah.
The black marks count against your congestion volume.
Yeah. So it counts it against your allowance.
So the more black marks you put in, the more you're charging yourself.
Yeah. But
so the incentive then is for your endpoints to control their, whenever they get a red bit coming back, they should lower their sending rate in order to
which
not
is
have to
what they're
issue
meant to do
as many
anyway.
black marks.
Yeah.
And at some point in the future,
Yeah.
you have to continuously issue them
Right.
when they first get the red marks.
Unless they're cheating, which is the
Yes.
incentive to say, oh, well, I'm just not going to put in black marks because it's going to penalize all my neighbors, and I'm only going to get hit with 1%.
But you know, I just want to be absolutely clear about this. All this crap doesn't need standardizing. You know, this is an example of what an ISP might do.
Yeah.
It's just the first step is to add this information, and it's just a canonical example of something really neat and bulk that an ISP could do to incentivize the correct behaviours.
So, okay, it's sort of a rhetorical. Do you have a more technical question at this point? I have a rhetorical question. Like, when is this actually going to happen? I mean, we can't even agree to do ECN, right? And how long has it been now?
Right.
When did Sally propose it? 98?
So that's
95? Something like that?
The other problem is they're never going to give the last bit out of the IP header. It's just guaranteed, right? It's just never going to go. So
what?
IPv6 is kind of an entire ginormous, you can build a house.
Once they start turning off V4, it seems like, well...
How much aerospace you want?
Yeah, if you really believe V4 is going away, they should give out.
That's right, exactly.
Well, this is the argument we had last week. The IASG don't want to give away the last bit. So they've agreed we can do this in V6. We can do an extension header, blah, blah, blah. Since then, I had a sort of plan B, which is a bit of a hack, which essentially turns off fragmentation in V4 and then sets a magic number in the first 14 bits of the IP ID and uses the last 2 bits. Which, it's valid. It's as long as you don't have to do fragmentation, it works.
Yeah, in fact, at IETF, one of the discussions was around the IP ID.
Yeah, Joe touches thing.
Touches one.
It's precisely what Joe is saying.
Exactly. He said,
But used for
always
purpose.
said don't fragment.
Yeah.
And the flow ID it should only be used when you're actually fragmenting. It should be just left as zeros otherwise. That's basically what he was saying. And in other words, you should set don't fragment equals 1. And the flow ID should be left as zeros whenever it is a fragment.
And all this is doing is setting the flow ID to a magic number, not 0, so that you know it's for this scheme. And in fact, Joe's scheme also says you should have a small number like 2 or 4 bits, I think, that are cycling, just so that people realise that it would be broken if they tried to use the differences in IP ID. And this actually has 2 bits that would cycle.
I would love to use
Yeah.
the fragment ID as basically if I have multiple paths inside my data center, I'd use that as the extra entropy to say which of the
But we can do that inside the data center. Who cares?
Yeah.
Right. Then, I mean,
So-
it's like everybody wants.
We can do
But then
it.
So the question about
It's all abstract.
the question about why ECN hasn't been deployed, and why I'm being stupid enough to think this might be, is that I've been stupid enough now for 7 years, and I'm still trying, and that's because I think it's one of those things that I think the internet needs to stop it going the way that it went with NATs. Where we didn't have a proper solution to traffic management, to the address space problem or a deployable solution. So we got all these NATs. I think deep packet inspection shows we haven't really got a proper solution to traffic management. And so if we had a proper solution, it would, I think it would help the internet from going down yet another horrible rat hole where everything gets even more difficult with, the deep packet inspection stuff that our company does, you don't want to know. We now invent our own AAA protocols because we can just program them up on the DPI box. And we get our customers, and it just looks at the bits and says, right, that's one of them, well, send it there and all the rest of it. And we can just do what we want, and it sets the diff-serve code point on things to tell other boxes to do things, and it's just a complete mess.
So what happens? What's the difference between the situation today, where of course nobody's setting a black bit, and the red bit is arguably the ECN now? What's the difference between that situation and the situation where you have a cheater that never sets black bits? Do you get the same behavior?
Right.
Because if so,
no, there is a difference.
Do anything in V4, you said, well, maybe do it in V6 and treat V4 the same way as you treat a cheater, and that provides an incentive for people to move to V6.
Right. No,
That's really fine.
That will, whoa.
Right. The part that's missing out of that,
Like a V600.
I mean,
I was going to say you're confident.
yes, we could just
Not allowed to mix it.
we could just do this in V6 and make it really nice for V6.
That's why we got it.
But actually, the thing that's missing is you identify your traffic as Connex traffic. So there's non-Connex traffic and Connex traffic, and then Connex traffic can either be cheating or not. Do you see what I mean? So as well as black and red, there's a colour that isn't existing traffic, that's grey. You know, but if existing traffic is white, there's black, red, and grey is Connex traffic that isn't marked either black or red. Do you see what I mean? And so if I'm
what happens when somebody cheats is you end up dropping by shrinking the gray area in the middle where you had black at the top and red at the bottom. You shrink the gray area, and by shrinking it, that's causing drops.
Yes.
And so, well, today, if there's not congestion aware, then you're causing some drops, and you're shrinking that because it's all gray, right?
Yep.
And is that basically the same behavior? That's what it was.
No, but what?
Well, maybe you don't fix it in V4. You fix it in V6, and you get better behavior.
I mean, you certainly could do it like that if you wanted to. If you believed that network operators' interests were mostly about moving to V6, but I don't think they are. I think they care as much as the IETF cares about moving to V6. I think what I'm hoping they care about is their costs. You know, the sort of big fear and greed buttons. You know, and I don't think IPv6 is very high on their agendas, even though it might be on ours. So,
No, but it is getting there, though.
yeah.
And if they can control the costs because of deploying IPv6 or something like this, then... But I just want to go back to your point earlier. There is a surprisingly large amount of interest in solving this problem at the IETF. Even though people know that ECN is not deployed and all of that, there's still quite a lot of people that are very, very interested in doing something like this.
The thing is, ECN only really made a marginal difference to performance.
But we've never ever tried it on the real internet to even know.
No, that's true, yes. And certainly your TCP thing looks absolutely, rocky.
That's because we are only going to ever run it within a data center. We're not going to bother convincing anybody that they would ever run it on the wide area.
If BT can give us the money for now getting Sandvine, we'll implement this.
You guys use Sandvine as well?
No, we don't. We use Arbor, which was Eloquent, as far as.
Sandvine, they're the DPI.
But actually, Sandvine are quite heavily into Connex as well. I mean, Don Bowman is often on the list.
Yeah.
Because they know all our deep packet inspection vendors. That's the ones we use and the ones that want us to use them. They all see deep packet inspection going away because it was easy when it was peer-to-peer. It was like, even though those users are screaming, they don't actually really care that much about that traffic. And, so it's high cost and low value. Whereas once you start having to discriminate between, is this video high value to them versus that video? Because, when 80%, 90% of the traffic is video, you've got to start discriminating between videos. And you can't do that with DPI. You need an art critic.
I mean, YouTube versus pay-per-view,
Yeah.
right?
Yeah, who paid you more money, essentially?
Yeah.
Somehow you can figure that out.
Actually, there was a funny statistic that last year's ISOC panel, where they said the Japanese ISPs are claiming that P2P traffic is on the downward trend, and HTTP and HTTPS is on the upward trend. And I was just thinking maybe P2P is just masking itself as 443 now. It wasn't clear.
They said as a percentage, it is declining. they don't have, the study didn't actually have any data on the...
No, the absolute amount, the absolute amount is
Right.
staying about flat in most countries.
Because the Sandman guys are saying
Yeah.
that if it's encrypted, then they don't do DPI, they do traffic characteristic analysis and all that to figure out what's going on.
I've also tried to see whether possibly the reason it's staying flat is because it's being discriminated against.
Maybe.
Put in this here.
But I don't think it is. The Japanese studies seem to imply that that's not the case. But
So what would you need to actually implement this? Because it sounds like you don't just want to do TCP, you want to control, essentially mark all packets leaving a particular machine.
well, because this traffic identifies itself as Connex, you can do it an application at a time or transport at a time, and so gradually you. So TCP can go first, and then you can do RTP, or you can, and you might leave DNS forever, and never do it. So you would still have, if you like, permanent partial deployment where some stuff wasn't Connex and never would be Connex, and the Connex stuff is given preference, if you like, by the ISP because they can control it, and maybe the non-Connex stuff is limited or rate limited or whatever,
So the reason
because it can't control it.
To start with TCP is simply because all the ECM is
Yeah,
already there.
it's already in the machinery. Yeah.
Plus,
Yeah.
nothing else is
Yeah.
guaranteed to deploy anyway.
And it's a very large proportion of the traffic.
Well, I'm just thinking like with V6, if you have to add an extension where to hold your other magic bit, wouldn't you want to put the ECM bits in there as well?
Well, you've already got them in the V6 header. Exactly. V6 and V4 ECM is exactly the same. So these extension bits are for the black marking, which doesn't change end to end. So you just need to be able to see it. You don't have to change. So the routers don't have to change. The only thing that changes in this is the end systems and anything that you put in the network to look at these measurements.
Yeah,
We should
probably.
break and then go to we have a conference room.
We have 4,
Okay.
5, 7
Yeah.
if you
Yeah,
want
that's a
to
good
continue
idea.
Did you want to
this.
just summarize, is there anything else?
Summary. Right.
Okay.
A metric, ambitious, but you noticed that.
Are these slides up on the web somewhere?
The talk is being recorded, so.
Yeah, it is. And I always put my slides on the web. They're not there yet, but they will be by this evening. Yeah. On my website. Yeah.
All we need is really one ISP to buy in. They seem to be.
Well, Comcast are very keen. Comcast are very keen at CTO level,
Yeah.
and Verizon are now coming out quite keen. Although not at corporate level, but people at the IETF seem to be. Dave McDyson and co. There's some that I can't mention because they talked me off list. There's a big one in Japan, the second biggest, who's interested at director level. And so
Okay,
Yep.
let's thank speaker.
Okay.